Hello everyone, my name is Jakub Kozłowski. I'm a Scala developer like you, and I'll be talking about concurrency, concurring concurrency, and functional programming at the same time. I'm really glad to be here, so thanks for having me, and I hope you have a good time. So, I want to start slowly, without any code yet, for like the next 4 slides or something. So let's just think about our world for a second. Just imagine for a minute, for a second, how many things are happening in the world right now. How many people are working, sleeping, well, doing work, driving, or having fun. And it's really amazing, incredible how many things are happening. And it's not just people. There are all the forces of nature also influencing the world and the universe. It's all at the same time. And, well, with that much stuff going on at once, we must be living in a pretty good simulation. But simulation conspiracy aside, we as developers, we need to be aware of that in the programs we write. We need to be aware that the world is concurrent. And our programs need to become concurrent as well. Because there might be a need for an application to support multiple users at the same time, or our program might have multiple sources of input that will be concurrently processed. Imagine a web application that only allows one user to be logged in at the time. It would stand no chance in succeeding. Or a modern sound editor that doesn't allow you to change the track you're listening to. It would be pretty annoying. So allowing concurrency is often a necessity in our programs. So if almost everybody needs it, what's the big deal? What's so hard about concurrency that we hear about the difficulties so often? It turns out that most of the effort associated with trying to make our programs concurrent is related to state. After all, because all of these events that take place at the same time, or concurrently, the world is changing all the time, and so is the universe, and that also has a reflection on the programs that we write, on how they work, what they do. And the programs that don't have any state, they are really easy to make concurrent, but we rarely see such programs. Even a calculator application on your phone, it has some state and it has some concurrency because you might press 2 different buttons at the same time. And the program still needs to handle that situation. Even though the concurrency is very limited, it's still there. For other applications that have more state, it might be a database, a message queue, an external system like an API owned by somebody else, or maybe the position of the sun. So there's lots of sources of concurrency and state. And the majority of programs will need to adapt to allow users to concurrently interact with them, because that involves touching the state in some way. And if you squint a bit, maybe you'll think that state is the only cause of concurrency issues. And on some level, it probably is. And by concurrency issues, problems, I mean race conditions, deadlocks, data corruption that might happen if you have 2 concurrent attempts to do something, or even application downtime, which can be caused by any of these issues. And all of these can have severe real-world consequences. So today we'll be talking about concurrent state, mostly, while keeping in mind some of these issues. And in particular, we'll look at the usually chosen solutions for managing concurrent state in Scala programs, as well as a purely functional new alternative. So if we think about functional state, maybe there is something that comes to your mind if you have been in the FP community for a while. We actually do have some tools for working with state in the functional programming world. We have a state monad. So why don't we use this? For those who don't know, the state monad is just, like you see, a wrapper for a function that takes the previous state and produces a new state along with some value of the type of the whole state. value. So it's really good at modeling local state, like multiple updates to a variable, which in this case won't be a variable, but a constant that will be just replaced with new instances of the same type in subsequent calls. But there's one big problem with the state monad. It doesn't work with concurrency. And if you know how state programs are composed together, then you'll see that this is a very sequential operation. There's no way to run two of these functions in parallel and expect a meaningful result. And if we can't even run them in parallel, then how do we make them completely independently concurrent? It's impossible. In the words of Fabio, by the way, I really recommend watching this talk and all the talks by Fabio. The talks are great and you can learn a lot. Passing something from a function to another is the most sequential thing you can think of. And this is exactly what happens when you run two state programs one after the other. Or if you try to run them concurrently, you would need to work around that. So this is exactly why we cannot use state for concurrent state, the state monad. So does this mean we cannot have concurrent state and functional programming and all the benefits of it? Well, absolutely not. So let's forget about FP for a second and focus on concurrency itself. Let's look at this line of code and think, what's wrong with it? And in a concurrent program, it's very wrong because if it's in a critical section, a place that can be accessed by multiple threads and it's using shared state, it doesn't make any sense. And to show you why, here's a bigger example. So we have a user card class. It's going to be shared between multiple threads. It will be like in the session or something. And we have a way to get the size of the card and to insert an element to the card. The card is powered by a list. And basically how we insert elements is we check if the element is already there. If not, we will append it to the card. Otherwise, we just do nothing. Now, imagine what happens if we run two threads that execute this piece of code, the same sort of data. They're trying to insert the same item to the card. Now, what will be the result of get size after these two operations? And we cannot really tell, because the put operation isn't atomic. It's not possible to run it in two places at the same time and expect the same result as calling it sequentially. So our concurrent calls can interfere with each other, and our result might not be 1. It might be 2, because we'll get the same object twice. And if we try to actually insert two different items to the card concurrently, it might turn out that only one of them ends up in the card. So this is a really bad situation. And the same with the counter. It might just not be incremented or not be incremented enough times. So what are the solutions for this problem? And where's the problem? So the problem is, of course, in these two lines, because that if doesn't ensure atomicity in any way. So what we can do, the easiest way to solve this in the short term is to add the synchronize keyword, which way we use a lock, actually. So the compiler or the language will interpret this as we want to have a lock on this object, and no two threads can call this put method concurrently. So this sort of solves our issue, because now we have deterministic inserts to the card, but it has some more issues, in fact. One of them is that it's blocking. So if we have 10,000 threads trying to insert, then one of them will be doing the work, and the rest of them will be blocked, and wasting resources and basically not progressing any further. And even if we time out the operations on these threads, well, it's not really that easy to interrupt them. It's also very easy to break by introducing some of these other issues that I mentioned before, like deadlocks. If we have, for example, a recursive data structure that has for example, a list, like head and another list as a tail, and we make a lock on the tail. Actually, a linked list would be a better example, but in recursive data structures, we could easily lock on the parent structure and the child structure, and they might be locked together. It's really not easy to reason about. And because of that, mostly, it's non-compositional, so we cannot really compose locks together in a sensible way, because sooner or later we'll just have deadlocks and other nasty stuff. And by compositionality, I mean what Runar meant. Software is compositional if you can understand the whole of it, of the program, by understanding pieces of which it is made and the way they are composed. Another solution very often chosen in the Scala world is actors. And while actors are a good solution to some of the problems, I think they are not the best solution for single machine concurrent state, especially in cases like this one. Because the actor model is advertised as something pretty simple and quite easy to use, and probably everyone more or less knows how to talk to actors. But in reality, it's quite a low-level construct. Even the streams in Akka streams are implemented with actors so that you don't have to touch them, at least the default runtime for them. So it's not just sending messages to other actors and not just covering the state behind the actor. It's actually, an actor is actually a finite state machine powered by a queue that can do all sorts of nasty side effects while processing any message. It can send more messages, it can create more actors, or change its own behavior for the subsequent messages. So it's a quite powerful concept and quite a powerful solution, maybe too powerful for our problem. Most of the reasons I've seen people actually use actors were as wrappers for mutable shared state like this, and not doing any more complex actor networks. Or limiting the amount of concurrency, limiting the access to some shared resource. And both of these problems have way simpler solutions. And the actor model also brings this push mindset. So now if you want to call a method on an actor, you don't call a method. You send a message and you hope that at some point you'll get a response for some of the messages. Like in input, you won't get a response ever. And this doesn't really clean anything up. And if you have a timeout set on that callback, let's say, on that second message that comes back to you, and you probably should have timeouts on asynchronous processes anyway, well, you might have a timeout on a simple get operation that doesn't even send any more messages, that doesn't even cross JVM boundaries, even if we forget about delivery guarantees for a second. And also it's complex in testing, because you need to stuff your actors into some test probes, and basically orchestrating an actor system to make it testable is not one of the easiest things about it. So I would just say it's quite clunky. But I'm not saying anything is wrong with the actor model in general, or with Akka in this case. But these are just things that I found about this particular example. So let's look at another solution, atomic references. So this is a thing that came with Java at some point. And it seems to solve all of our problems. We now have no deadlocks, at least not yet until we introduce another reference, or try to use it in the wrong way. So now we have an atomic put operation because we use the update and get operation on the atomic reference, which is, well, atomic. So if the card already has the item that we are trying to insert, we just return the same card as we had before. which is what we wanted. Now, I really need to find the bad reasons not to use it, right? So the first one is that it's side effecting. Like creating the atomic reference is a side effect. Getting the size of the card is a side effect. And inserting to the card is, well, probably the biggest side effect of them all in here. And it also allows us only to have synchronous updates, which might not be a very, very bad thing, but we cannot asynchronously compute a new value of the card in the update and get section. But as I said, this might be a good thing for some cases. And the fact that we have shared state, concurrently shared state, in this user card class is implicit. The callers of this user card class will never know that there is some shared state underneath. And they probably should, because that would probably make debugging easier. So my proposed solution, instead of just using atomic references, is using purely functional atomic references. So we have something like this in Zio, in CASEffect. This is the CASEffect version. So we basically moved all of our stuff from atomic reference to ref, which is a purely functional alternative. And probably the biggest changes are that we don't have update and get. We have just update, which takes a function from the old state and produces a new state. So it's sort of like it takes a state monad, basically. And there's another function called modify that actually allows you to return a result from that. That's more than unit. But there's still one bad part about it, or at least in some cases it's bad. It still only allows synchronous updates. There's no I/O in the update, the lambda pass to update, and there's no way of doing that. But there are reasons for it, it would be too powerful, I guess. And it's still possible to implement this sort of semantics with queues, but then you end up with an actor system again. So for this case, it's enough to do synchronous updates. And the most surprising part on this side is probably that creating a user card is an I/O. So if you don't know why we have to do it this way, here's a short introduction to referential transparency. So referential transparency is a property of purely functional programs, which basically states that if we have a program P and we replace all the occurrences of an expression X with its bound value, then the behavior, the meaning of the program and its value doesn't change. So in this example, if we substitute the usages of pi for its definition, then the result will be the exact same program, the exact same value as before. But hey, you'll say, this is broken. The moment we start doing side effects, it's broken. And I agree, because you shouldn't do side effects. And Future does it as well, because Future just evaluates eagerly and memorizes the result. But it works with I/O or task or Zio, because I/O monads in Scala or in any language, they're able to suspend the evaluation of a side effect. And thanks to that, we can keep referential transparency even though we have effects. But now they are not side effects, they are first-class effects. And this is actually why creating a ref needs to be suspended. It needs to be in I/O. Because if it's not, it would look something like this. There's an unsafe operator, which you shouldn't use, but it's just there for internals and for this slide. So if creating a ref wasn't effectful, if we just created a ref, like a constructor call, then, well, in this program, we will get a 1 at the end at the end of the world when you execute the prog value. So let's try to apply the substitution here. We'll replace the ref usages with its definition. And guess what? Now the behavior of our program changed. Now we have a 0, because we get a new ref in both of these calls. It is not shared. But we can actually work around that. we can use the same ref if we want with referential transparency. We just have to pass it as an argument to a function, or just flat map only once on the definition of ref on the value that provides a ref. And we can see that it makes sense and that it still preserves referential transparency if we replace this implementation of prog where it's used. So it's still going to return 1. And I cannot say this better than Fabio, so I'll just steal some of his slides. Basically, the important thing about referential transparency is that if you have resources such as this ref that are going to be shared between some computations, maybe concurrently, then we create a region of sharing by just flat mapping. The moment you flat map and you get out of your flat map, then your ref is lost. Nobody else can use it unless you return it in the flat map. But if you flat map on the same definition twice, you'll get 2 different values inside. And if you want to share, you need to do it explicitly. And it's really powerful, because the higher you are in the call graph, the higher you flat map, the more your ref will be shared. Your ref all, or whatever you actually use. It could be a cache or whatever. And it has this really cool property that the regions of state sharing are the same as the call graph. So you can just reason about your code, but by just looking at where a certain value is shared. And it's not dynamically determined by registering some state in a global registry and scoping issues. It's all very explicit now. And you can always understand it by replacing the value of an expression where the expression is used. And this really helps you control the way your shared state is shared. And as you may have seen in the card, if you have to pass a ref to the constructor, then it really makes testing easier, because you can sort of mock state in a very easy way. So long story short, referential transparency is useful because it gives us this ability to refactor without fear. We can just inline you can inline multiple usages of an expression, and the behavior will not change. Or we can extract some common parts, or name some smaller parts of our program and move them somewhere so they will be better understood. And it still retains the behavior of the program. And it's compositional, because now it works for really anything. You can write whole programs with referentially transparent values, like I/O values. And because we understand the way that I/O programs are combined or composed, you just have to understand the pieces and the way they are connected to understand the whole of it. And the dependencies between, for example, multiple services that use the same state, they become more explicit, and you have more control over them. And also the effects of any calls in your program are now also more explicit. They're first class. There's now no situation where you call a method that returns string, but it does a call to the database inside. It just will return I/O of string or f of string if you are abstract. And this is really good to know if a function makes a database call. So I mentioned Cat's effect. It's worth repeating what it is. It's a library from the Scala type level ecosystem. It provides things such as an I/O monad, types like fiber, which I'm not going to talk about too much today, type classes for describing concurrent effectful programs, as well as some concurrency primitives such as ref, which we've already seen, deferred, which is a purely functional promise that we are going to see on some of the slides, Semaphore, which is exactly the tool that people could replace their actors with. It limits the amount of concurrent access to a resource, or to a program, actually. And mvar, which is beyond the scope of this talk, but it's also pretty useful. So let's imagine we have this task. We need to build a combinator on 2 I/O programs that needs to fill these properties. If the left program completes first, we cancel the right one, and we want to keep the result of the left one. If the right one completes first, we just ignore it, and we keep the left side running. But if someone cancels our program, then we want the left side to be cancelled. And we need to preserve cancelability in all the possible cases. And there are multiple cases when we can hit cancellation, which is exactly the point of the next slide. So cancellation in concurrent effect systems in Scala, like Katz effect and Zio. Okay, I'll just let you enjoy this for a sec. Okay, enough. Cancellation is really hard. Like it makes things quite complex. But why do we even need cancellation? Okay, this is too distracting. So we need cancellation because I don't have a slide for this. But if you run 2 IOs in parallel and one of them fails, then you want to immediately cancel the second one, because otherwise you're just wasting resources. But there are some things that you don't really want to cancel, like you need to free up some other resources. Then you need to be in control of that. So cancellation is hard. And if we want to implement this function with the most basic, the most low-level operations on I/O, like start, and then you have to talk fibers and race, then there are so many ways that this can go wrong if somebody cancels your whole I/O. I found at least 3 places where this can be cancelled, and this is why we have all this exit case and bracket case and uncancelable. So all of these, each of these places could be the moment where somebody decides to cancel our program because something else crashed or we lost a race. And this is really scary, right? If you just miss one of these, or maybe there's one hidden here that I missed. If somebody cancels us, we might be wasting resources. So it's probably better not to write this sort of code and use something more high level, right? So introducing deferred, it's a purely functional promise that can not be failed. If you want a failure, you just have to define it for either with throwable or whatever your error type is. So deferred provides us 2 functions, get, which will complete after the deferred is completed, and complete that allows us to set the value of the deferred. And it can only be run once. So it's not like ref, it only allows us to set the value once, but then we can concurrently listen for it. And creating it also is effectful for similar reasons as with ref. So with deferred, we can implement our combinator in a way simpler way. Now we just use the operators that are more safe there, that handle cancellation on their own. And we don't have to touch fibers anymore. We just use race and the parallel combine operator. They are explained on the bottom, but it's not really the goal to explain all of this, just show you how things more or less compose. And now, because we didn't touch a fiber manually, this is perfectly safe, and this will not, if the program is cancelled at any point, everything will be freed up. So all the remaining running IOs out of these 2, left and right, will be cancelled if they haven't completed yet. And there's this is actually a piece of trivia. There is a piece of code, a function called memoize in the concurrent type classes companion object. And it does pretty much what we just did with deferred, except it also uses ref to ensure that, well, to ensure additional safety. And our implementation of the program also became a bit cleaner because now we don't need to complete and get manually. We just have a race and a parallel. And the interesting part here is that memoize returns a nested f, which might be surprising again. But again, this is because of referential transparency. Memoize is referentially transparent. So if you just call this method and you flatten on it, then every time you call this, you'll still get a different result. But if you flat map on it once and you use the nested value multiple times, it'll be the same value, which is exactly what referential transparency told us. And referential transparency is important in concurrency because it makes it bearable. Like, can you understand this? If you looked at this for 5 minutes, I guess you would understand it. But right now, you probably cannot really easily see what this does. But exactly what I said before, we can create sub-programs out of pieces of our program. So this is what is going to happen now. So this is the same code, and it works the same way. Everything happens in the same order because we have referential transparency. And I only introduced new vals that correspond to pieces of our program. And now all we need to understand is the smaller pieces, and wherever they are used, we need to understand what the operation that's around it does. So if we understand, let's say, if we understand register, and we understand the double shift operator, then we understand pretty much the whole flat map. And it's really cool. It's really powerful and really cool. So you can build your own concurrent structures, concurrent algebras, like we had ref and deferred and all of them that are basically primitives. And you can build stuff with them, like caches, circuit breakers, maybe internal job queues, or anything that's very specific to your domain, like bank balance or a player's health in a online game, and more. So I encourage you to learn this because it's really empowering. Functional concurrency is cool. This is my quote for today. So I encourage you to try it at home. Go to the Cats Effect documentation or Zio documentation, I don't care. Use IO in production as we do. Don't get discouraged because I know this might sound strange and scary at first, and it definitely takes a lot of time to feel comfortable with and feel familiar. So take your time and don't hurry too much. If you're looking for next steps, if you already understood this, you can follow these links. There will be a link to the slides after these ones. So I also encourage you to learn what FS2 is. It's a streaming library that also provides queues and topics, and also a bunch of concurrency-related stuff. And if you have any issues, there's something not mentioned in the documentation, just feel free to ask on the Gitter channel, and somebody will respond. Here's a bunch of links for those who actually go to view the slides online. And this is all I have. Thank you very much. Okay, I guess we have time for questions.
Okay. I have a question. You described one example related with card. I'll give you another example. Is more related to actor system to compare with your approach. So we have account shared between me and my wife, for example, and we both have credit card and want to withdraw money from one account. How you will use your approach for this special case?
Yes, I think you would probably want to use a semaphore so that you can't both spend money at the same time. Or, well, it's not going to block. You can use a semaphore without blocking any thread. This is also really cool about this. Maybe I can actually show a demo. because I think we have more time than we were supposed to. So let me just. Oh, not this one. There's a shortcut on Mac that I don't remember. Okay, I'll do it manually. Okay, can you see the code? Okay, bigger. So the cool thing about semaphore and all of these data structures in Classifact is that they are all non-blocking. So let's say we want to run 20 parallel operations, but we know that only 10 of them can run at the same time. So let's say our operation is IO of unit. It's IO. Oh no. So we want to run 10 of them at the same time. We can run 10 of them, but we want to run 20 or 1,000. So let's fill. Okay, so this is our operations. What we can do is par traverse. Actually, par sequence. And now they would just run all at the same time, probably exhausting our thread pool, like on John's example and first talk. But what we can do is use a semaphore. So I'll create a semaphore with 10 permits and flat map on it. And now I can use sem with permit. And yes, this will do the job. I think I need some imports. But other than that, oh yes. Yeah, something is missing. I probably need to extend the main. Oh yeah. Right. This. Oh yeah. IO. Actually, I really recommend you check out Metals. This is the editor I'm using, VS Code with Metals. It's really nice recently. It even has completions. Okay. Yeah, but these are accurate. No, IntelliJ is also really good recently. So I think I got something wrong here. No, this is a list. Yes, classes implicits, you're right. Okay, and now we are, don't worry, this is just a missing run definition. So let's create it. Oh, no, I cannot. Why does it suggest it? No, come on. Yes, it works, okay. So I can run this piece of code. Let's call it ops. Okay, and I'll run ops. Success. Okay. And if we run that, then yes, only up to 10 will be running at the same time, and eventually the whole thing will complete. IO up is another thing from Classifact. It just allows you to return an IO from your main, or run in this case, so that you don't have to unsafe run anywhere, unless you are interacting with like legacy code or Java code. Okay, so I think this is all I wanted to show and even more. So just to sum up, thank you. And if you have any questions, I'll be here for the next day.